Yo, what's up, what's up? Welcome back. Today we're working on my operating system. It's a toy x86 operating system written in Rust, and these are like its current features. So if I pop open a demo real quick, when I run this command, it's like building my operating system, packaging it in an ISO that's loaded into QEMU, a virtual machine. QEMU is logging that it's like, my operating system is logging to the serial console that it's like booted some CPUs. It's doing like some like demo shit where it like talks about like, hey, this is a vector, this is a map. I have allocations, I have containers, I've like found my network card, I can work with the clock, and I found a mouse. And it boots like this game up, and this is just like, oops, that's new. Never seen that before. Is that okay? Interesting. I've never seen that before. That's fun. Anyways, we have this like brick breaker demo. This is me controlling it with the mouse. It's also controllable with the keyboard, like this. Great. And we also have like a network stack. So if I go to the IP of this guy, I have like an HTTP server that's running. It says like hello, and I say hello, and it says hello back, and it logs in the OS that like it handled these HTTP requests on different CPUs depending on like which one's available. Blah blah blah. So that proves that we have like this like network stack that's using PCI, as well as like a USB stack for the mouse and keyboard, as well as like graphics writing to the VGA for this guy. There's lots of stuff going on. And today we want to work on USB. And we're trying to say that this is going to be the last USB stream, hopefully. So what we have so far is we've like written this like USB system that works with the mouse, and we have like a driver for the mouse that's set like when it moves, it like writes a USB packet to our USB system. It gets it back, updates the mouse position. Great. When I'm looking at this, I can tell that it's like really slow, right? Like this is really laggy, and I'm pretty sure that the cause of that is because we haven't enabled USB interrupts yet. So the idea is that when we write USB packets, the mouse driver, he sends a packet over to the USB system, I guess, USB. He says like, fill this buffer with my position, please. Position. The USB system talks to our like UHCI driver, which is a driver for the host controller card for USB. So the idea is that like here we have like a CPU, that's us, where our code runs. He's connected through PCI and memory to this like physical card, UHCI card. And this guy's connected to physically to my mouse. And so what happens here is we put this buffer, this like gets forwarded in code to like the UHCI card, who then sends out like the bits on the wire to like talk to the mouse and say, hey, give me your position. The mouse goes back, and then this guy's responsible for like taking like the stuff on the wire and turning it into like bytes in a buffer for us. Great. So what's supposed to happen is like that's going to take some time, right? Like this transmission on the wire is not immediate because like in order to transmit stuff, we have to like send data over time, right? So there's going to be some latency between when we send this out and when we get it back. And so what the interrupts are supposed to do is like here we have like an interrupt line, IRQ. And what's supposed to happen is when he's finished, he just goes like, doot doot, I'm ready, time to go, like I finished, here's your packet. But what we're doing right now is we just like wait for like several milliseconds before going like, I'll check again now, I'll check if the hardware is done. So that's the first thing I want to do is I want to like hook up this like interrupt feedback from the controller back to our operating system and hopefully like handle that in some reasonable way. The other thing I wanted to do today is the way this like UHCI card works is he has like, give him like a list of buffers or like a list of pointers, I should say. So this is 1024 buffers, and they're serviced at like 1 millisecond interval, I guess. So like you have like 1024 of these guys, and the USB card will like look at this one, and like 1 millisecond later he'll look at this one, and 1 millisecond later he'll look at this one. And the idea is that he will do work at least once a millisecond. But this mouse guy over here, he might say like, hey, I'm gonna give you an update once every 8 milliseconds. And so if we were to like put that work, like if our USB driver or our mouse driver was just to say like, hey, get me a mouse position, he'd like put, I've missed something here. We have like this like queue over here, queue of work. And so like our mouse driver will like put a thing in this queue of work every time he wants to do something, every time he wants to get the position. And what we do is we point every single one of these elements at the same queue. And so that means that like our queue will be serviced once per millisecond, essentially. But if our guy says that he wants to pull at 8 milliseconds, what we have to do is we would have to like make a new queue that's like Q8 over here, and we would only want to point to this guy once every 8 of these, so that he gets service like once in a while. So that's the second thing I want to work on, is I want to fix like this queuing system so that our mouse driver can say, hey, I want a lower frequency polling. And then if we get that done, there's like a couple other things to clean up, specifically like endpoint piping. So we don't handle parsing of endpoint descriptors right now properly. We just kind of assume endpoint 1, and that's going to be a problem. And then next up, if we finish all of that, we could stress test our USB system by trying to write a keyboard driver to prove that we can have like multiple USB devices working at once. So that's the plan for today. Got a few messages in chat. What's up, you guys? Is this like a Unix? Well, that's like kind of undefined at this point. So I think if I understand correctly, what makes a Unix operating system is like the interface that it gives to user space applications. I think like POSIX is the standard I'm thinking of, and we don't have any user space at all right now. So there's like no interface between our operating system and programs because programs don't exist yet. So whether or not this is going to be Unix-like is like undefined. I assume that if I were to get to the point where I wanted to like use this thing for more than very, very minor toys, it would make sense to make like at the very least like a POSIX compatibility layer. So that like if I wanted to like run Python, I wouldn't have to write a Python interpreter from scratch. I could like use one that exists. But whether or not like my operating system is going to be Unixy, I don't really know yet. We'll see when we get there. Is EHCI next? Probably not. I think that the chance of me wanting to do USB 2.0 right now is like pretty slim if I get the mouse working. I think probably what's next is, well, I don't really know. There's a few directions I could go. Maybe I'm thinking either working towards a user space. There's like some like driver init cleanup stuff I want to do. There was something else. File system is probably something else I would want to do. But I haven't figured out what I want to do next, so we'll see. Can you make it able to open ELF and PE at the same time? What's PE mean in this context? That PE, position executable. No, that's pick. The Windows thing. Oh, yeah, I don't know. I probably would lean towards ELFs, but I don't know. We have to think about it. We have to think about it. We're pretty far from getting there. But yeah, I'll see. We'll see. Okay, so let's get moving on some of the stuff for today. The first thing I want to do is work on enabling USB interrupts. So enabling USB interrupts is the next guy. Okay, so if I remember correctly, when we worked on our network driver, he had kind of like a similar hookup to the CPU where these lines would also go to like network, and we have like both the PCI and memory are also connected to network. And if I wanted to get like the IRQ number, if I remember correctly, there was like an interface that we could ask from the PCI system to get the get which interrupt would be fired when this guy talks. Would I implement my own file system or like an ext2 driver? Also don't know. Yeah, not sure. I probably would have to at least do FAT32 for interop with everything, but I haven't really thought about it too much at all yet. Okay, so we know that the network card has interrupts of some form, and so we can kind of look at what we did in our code here on initialization and try to find where we figured that out. So here he has like get IRQ ID from the PCI interface, which comes from general PCI device. And what does that guy do again? It's been a minute. He says get IRQ num, which just reads register 0xF from PCI space. So probably if we go to the PCI OS dev wiki page, probably we'll find a general PCI device descriptor. Here we go. And we're reading interrupt register F, which is this guy, and this guy has an interrupt pin and interrupt line on him. So we're reading bits 0 to 8, so we're looking at the interrupt line. And there's interrupt pin as well. I don't remember which is which here. Interrupt line specifies which of the system interrupt controllers the device's interrupt pin is connected and implemented by any device that makes use of interrupt pin. For x86 architecture, this register corresponds to the PIC IRQ numbers 0 to 15, and not the IOA PIC IRQ numbers. Okay, perfect. That's what I'm looking for. So, then in what do we do here? This gives us back like a number, and here we convert that into a like PIC thing. So the idea being is that the interrupt controllers in our CPU, we have like CPU, I guess we'll draw it smaller. We have like the CPU, and he has like interrupt lines going to an interrupt controller. And this interrupt controller has like, I think he has 8 pins on him. So he has like 0, 8 to 8. But we want more than like 8 serviceable interrupts. So one of these guys goes out to like a second controller. That has 0 to again. And then these guys like daisy chain together to give us interrupt IDs 0 to 15. Right, because we lose one because of this interconnection. This is saying that if we like talk to a PCI device, one of the like interfaces that all PCI devices give us is like which of these numbers we're hooked up to. And we have like some of this is implemented directly in our network card, which should probably be brought out into the PCI stuff. So we'll change this guy here. He returns just like a raw number here, and we'll just return it, convert him into an IRQ ID, which is like which of these guys are you connected to, if any at all. So we have to include interrupts IRQ ID, and we'll just kind of slap this guy directly into this function. So this says IRQ. This is no longer called IRQ num, it's called IRQ. Great. And I guess this can fail because the IRQ might be an invalid number if we get back from PCI. So we'll just pull out this error type and slap it in here. And this get IRQ num will now return a result of IRQ ID or invalid IRQ. Sick. This guy can go away. And this is now just RTL device get IRQ num PCI. We're close. This is as U8. And this guy needs to pull in invalid IRQ. This is the error is defined somewhere else now. Does that compile? Sure does. This guy doesn't need the IRQ ID type anymore. We cargo format because we didn't get the formatting right. We run our lint scripts. Give it a sec. unit test pass, everyone's happy. And if we run, we should still see, the test here to make sure that this is all working right is if we use the network card in any way and it still works. So this guy's up and running, and if I just go back to the IP, yep, sure is working. Okay. So we'll just quickly commit that as I don't know. I'll think of like the titling and naming for this later, but I'll just call this checkpoint IRQ ID refactor. Okay, so now we have like an easy way to pull out an IRQ ID, and we use that ID to register with like the interrupt system. So in our UHCI stuff, I guess first let's just see if we get a valid one. So in our initialization code for this guy, we'll just say print line, or I guess we'll info log it. We'll say, oh, sorry, this isn't here. This goes in the constructor, actually, where we have access to the PCI system. So here we'll just say interrupt number for UHCI card is this. And here we say device dot get RQ num, and we pass to the PCI bus. And I guess we'll just unwrap it now for now to see if it exists. And if it doesn't exist, then we'll crash. So we can cargo run and see what happens. Oops. This guy doesn't implement debug, so let's just fix that real quick. So we can print them. And let's see what we get. Interrupt number for UHCI card is pic23. So we did find a valid interrupt, which is sick. Which means that on construction, we can probably just register an interrupt handler. So the way that our interrupts work is CPU has an interrupt table. Let's just make this canvas a little bigger. Okay, so CPU, he is connected to like this like interrupt table in memory. So this is like interrupt vector table. And what happens is when like an interrupt fires, he'll get like IRQ10 comes in here, and he goes like, ooh, 10. Let's see if there's a number 10 in here. And so he'll like look at the 10th entry in here. So he'll be like, ooh, entry 10. Like, let's say this is 10. I know that it's not because I didn't count right, but we'll assume that this is 10. What will happen is this will have like a pointer that we put in. We'll be like 1, 2, 3, 4. And it will like take that and it'll be like 1, 2, 3, 4. That's like an address in memory. So like if this is at address 1, 2, 3, 4, he'll just be like, womp, I'm going to go like execute this code now. And so what we've done is we've hooked up this vector table so that all of our entries point to the same point in memory. And that point in memory, like what it does is it does like a lookup for the interrupt number. We do have like a little bit of injection of like code here to like call this area of code with the interrupt number as an argument. And then we can just look up our handlers and like run it from there. Quick question, how do you get KDE to tile your windows like that? Oh, this actually isn't doing any tiling at all. I just like right click this and I say like no title bar and frame and then move it around. Which isn't great, but shit, how do I fix this now? Is this unfixable? All right, I'll just close this. No, I want to keep this open though. Fuck. I guess this window will just have no title bar and frame. Oh, not your bad. It's fine. Don't worry about it. Okay, so our UHCI system, we're going to want to like register an interrupts. So we'll just say we pass in like interrupt handlers as a interrupt handler data. And here we can just say interrupt handlers register, and we register the interrupt ID. So we say let RQ num is this guy that we pulled from the PCI system. And we register him. And we pass in a function that we want to call at when that interrupt fires. And for now, we'll just say, like, hi, Mick, for now. So what we want to see here is probably nothing. We just want to see nothing crazy happen. Oops, we need to pass in the interrupt handlers when we construct our UCI driver, which is just here. Okay, and I guess this is a failable thing, so we'll just expect failed to register interrupt handler. Cool. Cool. Oh. That's interesting. Interrupts should only be registered once per interrupt. Where the fuck does that come from? Should only be registered once per interrupt. So this comes from when we register, we assert that it's the first time that we've registered that interrupt handler. That's interesting. So who else would be using this interrupt ID? We know it's a pick2 guy. I guess, is it possible that all of our PCI devices are plugging into the same interrupt number for some reason? Or is this like a settable thing? This table is applicable, blah, blah, blah. Interrupt line specifies which input of the system interrupt controllers from the interrupt device's interrupt pin is connected to. So this is like a physical connection to the thing. So I think that we can't just like change the number unless the PCI, unless it's like connected to all of them and it gets to pick. Can we like, well, first let's see who it's conflicting with. I'm going to assume that it's conflicting with the network card because I don't think that we've actually registered that many interrupt handlers. We've registered like, there's the real-time clock, which is using pick20, so that's not it. PS2 controller, which is using pick1. So it's got to be this guy. It has to be. What we can do is we can just disable the RTL interrupt handler for a second, just to see if that we pass that error. Okay. So our entire world is collapsing. That's cool. We're also getting a lot of high mix, even though we haven't enabled interrupts on the USB controller. So I think that's like a pretty good indication that the network card and the USB card are at least like claiming to share the same interrupt. Well, I'm going to disable interrupts on the RTL8139 for a second, the network card, just to see if that prevents all of that crashing, which it does. Okay, so howdy, I love x86, but I do not love Rust. I think that there's a, I think that low-level developers often don't like Rust that much. That's fair. And I'm pretty sure I would like, if I were to guess, I think I would probably guess why you don't like Rust. It, like, imposes a lot on you, and you have a lot less control. I'm a C guy myself, tried Go once, never again. Yeah, that's fair. That's fair. Yeah, I came from like the C++ world. Well, C as well, but mostly C++. Is like where I did like most of my working life. And Rust is like C++ on steroids, but man, the people who like, if you like the simplicity of C, you're not gonna like Rust. It's like probably that's fair. But if you like if you want all the features, it does have a lot of features, which is kind of nice. But yeah, I see the appeal for C as well. That language is super fun. It never does anything like unexpected. When you write like C++, you're just so often like things just happen and you didn't understand why. Where in C, like that never happens to you. like you were in full control, and any mistake, you're like, oh, that was my fault that it broke. Instead of like in C++, I often feel like it's like, and Rust, I feel like it's like, oh, I didn't understand, and how the fuck was I supposed to understand? Okay, so let's try. We'll I guess for now we'll start by keeping the network card just completely disabled, and see if the USB card is in fact triggering the same interrupts. So probably what we would want to do here is enable interrupts on the UHCI card. So here we'll split out like a self-enable interrupts. And what's this guy gonna do? Enable interrupts. He's probably going to write some register on the UHCI card. Probably. What are you using for reference when implementing everything? Any book or basic guidelines? Okay, so the only book I've looked at so far was when I started on USB, I was like pretty fucking lost, and I looked at this book, USB, the Universal Serial Bus book. This book here, pretty sick. Really like walks things through for you. And so I did find, this is the first time I've like ever read a programming book, really. And it was like way more walkthrough-y than anything I've worked with before, which is pretty nice. But otherwise, I've been browsing the OS Dev Wiki. This is pretty good resource. And then it will often have like links to real specs and standards at the bottom, and so reading through those when the wiki isn't sufficient is also pretty useful. Okay, so I'm trying to enable interrupts. So probably this guy, USB inter. That sounds right. Interrupt enable register. So probably I just write, what I'm looking for is interrupt on complete is probably the thing I'm going to try to set up first. So I think I just write bit, where was it? Bit 2 on offset 4. Okay. So self.io range write, this is a 16-bit register, yeah. Write 16, IO offset new, and what was the offset here? 4, I think it was. And we're writing 1 shifted left by 2. Did you stream yesterday? No, I skipped yesterday. Usually I don't think I've skipped 2 days in a row yet. The schedule seems to be some form of like 2 to 4 days on, 1 day off. Yesterday I just did some like off-stream cleanup that wasn't really very exciting to do on stream. Okay. So to enable interrupts, this is all we do. And then we have to say, in these like transaction descriptors that we pass to the, that we give to the UHCI card, one of the things that we can tell it to do is interrupt on complete. Like when you are finished this chunk of work, please fire an interrupt. So I think that right now if I enable interrupts and I don't set that flag ever, we should get no interrupts fired. And we should never see that print line that says hello. Which is true. And if I wheel the mouse around, the mouse is moving, but we're not seeing any interrupts. But if I set that interrupt on complete flag, so probably when I like set up my chunk of work, probably on the last bit of every chunk of work, I want to look at the descriptor and set interrupt on complete. And now we should see every time like a USB transaction finishes, we should see that interrupt fire. Okay, so we see some massive, massive corruption. But that indicates that almost certainly the interrupt's firing and just like fucking some shit up. Yeah, so it's like rapidly firing. And if I were to guess, I would guess that there's some sort of like stack overflow happening, and we're just like, instead of printing what we're trying to print, we're just printing like garbage memory and printing forever. I think I've seen this before when like interrupts fire too fast. You could imagine that like your interrupt stack just keeps growing and growing and growing and growing because you're not like servicing them fast enough. And you just run out of room eventually. That would be my guess. There's probably a way to prove that, actually. That'd be kind of fun. Let's see if we can prove that. So I guess we would write some assembly to pull the stack pointer out. So we could probably do like a move ESP into EAX and then tell this guy that we're using EAX. So we'll say out. I think this is the syntax. Out EAX. And we'll say let mute val equals 0. Yeah, this looks like it'll do it. And this is a U32. This goes in unsafe block. And then we can print the stack pointer. So we'll say stack pointer. And I guess we'll print it as hex. And we'll print val. I think that's right. I think... We'll see. I think what this will do is this will generate some code where by me writing out EX val, it'll like the Rust will like put some stuff outside of the assembly that I've actually written and go, oh, make sure to back up EAX to the stack. Then we'll print the stack pointer, and then it will automatically generate some code to like clean that shit up. I think. Let's see. Okay. So before all of this, oops. Oh, what am I doing? This is just the wrong area. Sorry, it should go here. I don't know what the hell I was talking about. There we go. But now, now we should see it. Yeah. Hey, that's kind of cool. We do see it like steadily decreasing, which is like a good indication that like my guess of Stack Overflow is correct. And I think probably it's because we're not like clearing the interrupt. So usually what you have to do is you have to ask the controller to like tell the controller like, hey, I fucking know, like chill the fuck out, please. So probably this guy, status register, write to clear. So probably I just write 1 to the interrupt section and it'll probably stop. That's just my guess. We'll see. I think that I don't know if I can write to the status register from the interrupt context without cloning it. Okay, here's what we're gonna do. Usually there's like some like type stuff to keep track of here, but instead I'm just going to quickly log what my interrupt number, or not the interrupt, sorry, the IO range is, where I'm like writing to like write these registers. So I'll just say info UHCI IO range is this, and we'll just log IO range. This guy doesn't implement debug, so we'll just have to fix that real quick. We're just shortcutting to try to like investigate. That's the plan right now. Oh god, we're still, oh god. How do I get out of this? Hold on. We have to disable the interrupts again. Or yeah, where enable interrupts. Enable interrupts. We'll just disable this guy real quick. Okay, so this is the address of the where our IO range base pointer. And so just for now, we'll fix this later, is we're gonna do another ASM block where we say this is the base plus what's the status offset? 2. And we need to write like some ASM to just write to that. So this is the 16-bit write. he says out the thing in AX to DX, and we say in DX is the address, and in AX is the value I want to write, which is, I guess, 1, because we're trying to clear that status thing. Now we could try enabling interrupts again, and just seeing if those guys survive. Right? Hopefully we don't see that like Stack Overflow shit again, because hopefully the interrupt's firing like way less frequently. Okay. So that's good. Like we see that like now instead of this guy like blowing the fuck up, he's staying pretty constant. We're not crashing anymore. And we are seeing that when I move the mouse, we are immediately getting like an interrupt fired. So I think that that's like a really good indication that we've confirmed that, one, the network card and the USB card are sharing an interrupt line. And we've confirmed that we know how to like write the interrupt flag, and we know how to clear it, which is pretty cool. And so what's the next thing to do here? The next thing to do would be to hook up the interrupt flag to our like futures. Yeah. So the way that works is right now when we like write a transaction, let's see if we can find this. Maybe append work. So when we write a transaction, we say, here's a bunch of like, here's some like USB packets that we want you to send over the wire. And some of these are going to be like read packets, some of them are going to be write packets. But the idea is like we send back this feature that says, when this feature is complete, those pieces of work are done. And what we do is like every time somebody wants to check if that work is done, we say, hey, are you done? Here. We read like a register from, or we read the descriptor back, and the hardware promises that like he'll set this bit or he'll clear this bit. I think he'll clear this bit in this descriptor when he's complete. And we say like, hey, if you're not done, like wake me up in a little bit. And what we have to do instead is replace this with registering our waker handle. So if we say like, hey, it's not ready yet, we like take a fucking nap, right? We're busy, like, okay, fine, we'll wait. And somebody has to tell us that it's time to check again. And so what we do is we like, our future has this like waker thing, this handle to like a thing that can wake us up. And we have to like put that somewhere that our interrupt handler will be able to like look at. And so how do we want to handle that? So it gets a little tricky because our interrupt handlers can't use our like normal synchronization primitives. We can't like use like mutexes in a interrupt handler. Because if you like interrupt while the mutex is locked, you'll just like immediately deadlock. So what we do instead is we usually when we're interacting with an interrupt handler, we work with lock-free queues. And then do some of like the more complicated stuff later. So probably what we could do, just for now as a test, is we'll make like a lock-free queue that the interrupt handler gets one end of, and we write to it from our end, and it reads from the other end. So I think we have lock-free queue is implemented as sender receiver. Great. So we can say we have a here, I guess. Sorry, one second. There. Here we have lock-free queue channel. I guess we want to use self sender receiver. We'll make a lock-free queue and we'll take the sender and we'll put it over here and we'll say waker sender, waker tx we'll call it, is a sender of wakers, which comes from core task waker. Now we'll say that our waker tx, waker rx is a channel that we get from our lock-free queue. And I think this channel thing takes in an argument of like how many elements that we're allowed to put in here. So we'll just like say 50, just fuck it, we'll put a number in here. This is all temporary, right? We're just trying to prove out the concept. And I guess in our interrupt handler, we'll try to pull from this guy. So say waker rx dot pop. Yeah, okay, so say the one-shot channel we made isn't lock-free, right? No, that used a mutex under the hood, I think. Yeah, he used a mutex. So I guess for now, I think it will assume that if I just pop this, it's okay. So we'll like lose the waker after we interrupt one time, but probably anybody who's sleeping will register their waker again. So it's probably not a problem. And so we'll just say while let some waker is equal to waker pop, we say waker wake, and then we put waker tx in here. He doesn't know the type for some reason, which is odd. Do I have to inject it here? So I guess we just pass in waker like this. Okay. And then in our future, we'll just say waker tx is a waker tx. Oopsies, this is a sender of wakers. And we'll just say self.waker tx send the waker. That seems right. No method send found on this guy. What does he have? Push. Okay. Sure. All right. Now, just when we construct this guy, we need to like propagate the waker. So here we just say waker tx is the reference that we have to our waker transmitter. And I think we're chilling. So let's see now if I understand all of this correctly. I think that our mouse should move a lot faster now, because instead of sleeping for some arbitrary amount of time, it should immediately get response. Oh, and look at that. It's so smooth. Oh my god. That's so much better. Holy shit. Okay, and it probably goes even faster if we stop logging the stack pointer every time, because that's probably taking up a significant amount of time. So let's just shit that out here. And quickly check this again. God damn. Okay, so that's pretty cool. I was fairly confident that if we did this right, it would become a lot faster, but this is like night and day. Holy shit. Yeah, well, I guess what we can do is we can we'll commit and we'll say checkpoint proof of concept USB interrupts. And we'll go back commit just for comparison. And this is what we had before. It's like, it feels like maybe like 1 frame per second on the mouse. It's so bad. But now, if we look at the current version, give it a sec. Oh, it's so smooth. Oh, baby. Yeah, okay. I'm pretty happy with that. So what have we learned? We've learned that the interrupt lines are shared. We've learned what we know that we have to like handle this like IO range thing. So we have this like we're bypassing some like of our safety checks with this manual assembly, as well as putting in the address directly. We don't want to be doing that, so that's one thing we have to fix. we had to disable the RTL8139 interrupt handler, or else this doesn't work. But otherwise, it seems okay. And probably we need to like think about this channel again. I'm not sure if this is how I want to do it, but maybe that's okay for now. Okay. Thinking. So the first thing to fix probably is this, like, the fact that we can only have one interrupt handler for an interrupt. This is, like, unexpected that multiple different classes, I should say, want to use the same interrupt handler. That's surprising. So the question is do I want to be able to register multiple and call both handlers when that interrupt fires? Or do I want to force that, like, the RTL8139 and the USB controller know that they share an interrupt and negotiate between themselves? I guess there's no guarantee that they'll share an interrupt. That's just like they happen to, but we don't know that, like, on all computers that'll happen. So it makes more sense for the interrupt handlers to allow us to have multiple. So here, right now we have our interrupt handlers are a map of interrupt IDs to a, like, function that we can call. And I think we just wrap that with a vec. Say we can register multiple. We remove this restriction that only one guy can be in there, and we'll say handlers, ID handlers are handlers entry, I think is the API here, for this key, which is interrupt num or default, right? So if there's no vector inserted in there yet, we'll get one, we'll make one. And here we just say ID handlers push function. Okay, and then certainly there's a compile error on use somewhere. So we'll say let functions is this, and we'll say for f in functions, call f. Wow, that was quick and easy. Now we just have to make sure that these interrupt handlers that we have are doing something sane. So this is clearing the interrupt, and probably we should only wake up our Ethernet driver stuff if the interrupt was there. So I guess we just say here we'll return if the interrupt was fired. So probably we'll have to look at the RTL8139 docs or interrupt handler how will you know which interrupt to call or interrupt handler looks good? So I think we just call them both, and each one internally will check if the interrupt status flag was set. Because, like, if I remember correctly, this guy should have somewhere on here. He should tell us if the interrupt was fired. So when we, like, clear the interrupt, we should be able to just read the flag that we're clearing, and that should give us a clue. So interrupt status offset is 0x3e, which I think in this document was like 3e h. Yeah. And here, what does it say? He says receive okay, transmit okay. And we're writing the number 5 here. So that's 4 plus 1. So we're looking for transmit okay or receive okay. So we'll just check. We'll say let value is equal to this, and we'll say if val and this are greater than 0, we'll return true. So I guess we just return. Oh, I guess we just save this before we write it back. Fuck. Nope, we don't. We'll just return val and that are greater than 0. And so now in our interrupt handler here, when we clear the interrupt, we'll just say interrupt fired. If interrupt fired. If the interrupt wasn't fired, then we don't do the rest. Cool. There's a race in here probably, but I think it's really short, so I'm not really too worried about it. I guess we can say note slight race if interrupt fired. No, it's fine. It's fine, it's fine, it's fine. I'm pretty sure. Okay, so now in the UHCI card stuff, we can read the status port. So here we'll say in. How does this in thing work again? It's in DXAX. And DX gets this. AX is an out value now. And we'll say let val is equal to 0. I guess we don't write equal to 0. We'll just say let mute val is a U16. And here we write val. And so now we can check if the status flag was set. So what is the USB status flag? 1, I think? Yeah. If val get bit 1, 0, sorry, it's the lowest bit. Yeah. If this bit isn't set, then we return. Interrupt wasn't fired. That was a network interrupt. And I think that's pretty much it. Let's just clear out some of these warnings. These guys aren't used anymore. We're not using the time in this UHCI feature, which is sick. So we delete these. And here we'll just say, we'll crash if the USB queue too short. USB waker queue. Okay. Seems reasonable. Okay, so the mouse is still working. It's moving snappy. And now, hopefully, the Ethernet stack is working too. And at the same time. Okay, cool. Cool, 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 cool. Okay, so the last piece here is that we have these, like, all of our, like, I/O operations go through this, like, I/O allocator. And the idea is that, like, we don't want different drivers trying to write to the same registers because they would, like, corrupt each other. So we do this thing where we, like, allocate this, like, I/O range, and we use that to, like, guard all accesses. And we need to use this in we need to use this in the interrupt handler as well. So, or do we? Sometimes what we do here is the interrupt handler, we just ask it to wake up our service function on our driver. And then our driver handles the actual, like, working with the status register and stuff. I don't think I want to do that right now because I think that piping the UHCI service function will be, like, a little bit tricky. So what we'll do instead is we will just split up the IO range probably. So this isn't trivial. This isn't trivial at all. This is annoying. USB status offset. So where does this guy even use? Clear USB status. Ugh. Oi, oi, oi. So, like, our interrupt handler somehow has to get this guy. I guess we'll do a stupid thing right now. I was gonna say that we could, like, just stick it behind, like, an interrupt guard or something, but I don't really want to do that. Oy. I guess I'll just bypass it. Fuck it. I don't really care. So maybe what we'll do right now is we'll just make like a pub function adder that gets the U16. And we'll just make this an unsafe function to make it clear that like we're bypassing some of the safety of this guy. And we'll return self adder. I guess we don't even need to do that because we have the address here. We have this IO base. So I guess we'll just use that. So we'll say note, not using the IO range abstraction because piping of single mutable writer is too difficult. This status right should be atomic anyways. Okay. And so what we'll do is we'll just keep these assembly blocks in here, but then replace this with IO base, which I think is a U32. Yep. And I guess we'll just cast it to U16 down here so that we don't have to do it here. And maybe we're chilling now. Maybe we're chilling. Yeah, that seems fine. I'm not like incredibly happy with that, but it's good enough for now. Good enough for now. I don't want to like spend too much time on this because I want to move on to other stuff. So we'll call it a day. Cargo format, cargo clippy, lint. Make sure that everything's good, ready to go, and everyone seems happy. So we can say git status, quickly check the diff. Is anything in here crazy? Nope. Oh, I guess it's git diff from one back. All of this looks fine. Okay. So we'll add everything, we'll commit, we'll smiley face it, and we'll rebase from a couple back and squash it and change this guy to say proof of concept USB interrupts, and we'll say, what are we doing here? We added support for multiple interrupt handlers for a single interrupt number because the UHCI and PC and RTL 8139 cards share an interrupt line. Then updated UHCI stuff to use interrupts on completion instead of polling based off a 256 hertz clock. Cool. Cool. So I'm happy with that. What's up next? The next thing we want to work on is what's it called? Multiple polling rates in USB. Okay, so the idea here is that let's see, what's the easiest way to talk about this? So my mouse is going to ask for a specific polling rate. Let's see if I can figure out how to log that. I guess in the mouse driver, nope. In main, maybe we construct the mouse driver. Yeah, let's just print line, or we'll info log mouse descriptor, or we'll USB descriptor. He has this guy just for now. And what we should see here is one of the descriptors that this guy talks about. We'll say, oh fuck, I need to pipe this into less so that we can see the underline. Configuration, interface, oh, oops. I'm actually not logging them all. Give me one sec. One second. Okay, here. So this USB endpoint descriptor is retrieved from like when we like ask the mouse about itself. We say like, tell me about yourself, please. And he says like, hey, I have like this interface, and this interface is like a boot protocol mouse. And then when you say like, okay, tell me like where I can talk to that mouse, he returns back like, hey, this is my endpoint address, and please poll me every 10 milliseconds. I'm pretty sure that's what this means. Let's just double check. So this will be in the USB endpoint descriptor stuff. So let's see. Endpoint descriptor. Configuration, endpoint. Interval. Interval for polling a device during a data transfer, expressed in units of microframes for high-speed devices and frames for low and full-speed devices. The exact meaning of this value depends on the endpoint type and the operating speed of the device. This field is used to calculate the period for full and high speed. Full and low speed. Field must range from 1 to 255. Dude. What the fuck? I guess it depends on which type we are. That's annoying. Expressed in units of microframes for high-speed devices and frames for low and full-speed devices. So this is in frames, probably. So this probably means I should pull every 10th one or something. Ugh, that's confusing. I thought I understood this earlier. Is like the USB spec going to give me a better definition? Configuration descriptor. Endpoint. B interval. Interval for specifying the endpoint for data transfer. Expressed in 125 microsecond units. What? Okay. So I guess in my case, it is just asking me to poll every millisecond, if that's true. I guess this is the USB 3 spec. I wonder if there's like a USB 1 spec that I could also be referencing. Because that, yeah, let's see. USB 1. Does this guy link? Maybe the 2.0 spec will also tell us something. Let's see. 2.0 spec. What does he say? Oh my god. Oh, that's a lot of words. Are any of these like high-speed interchip, USB 2.0 material, ECN, power management? Oh, this is the one. USB 2.0 PDF. And this is probably what I'm looking for. Endpoint descriptor. He says interval. Interval for polling endpoint for data transfer expressed in frames or microframes depending on the device operating speed. Either 1 millisecond or 125 missing character as units. Dude, that's so silly. That's probably like a mu symbol that like my document renderer can't render. That's good. For full high-speed isochronous endpoints, I'm an interrupter. For high-speed, B inner value is used as an exponent. For low-speed endpoints, the value may be from 1 to 255. But what's the unit? Oh my lord. Okay, so where does it tell me the operating speed? Okay, so I guess what they're saying is this is a if I'm a high-speed device, then I'm 2 to the n. But I'm probably not. I'm probably a full or low-speed device. And it's saying that this is either going to be in 1 millisecond or 125 microsecond units. So I guess. Oh, God. That's so annoying. That's like a lot to parse. I wonder if the Linux kernel will give us any clues. So we'll look at the USB mouse. USB mouse. And how does he know his interval? Endpoint B interval. Where does this come from? Does he set it? No, the USB system probably sets this somewhere. Okay. USB. Aha. Okay, wait, this looks... Oh, no, that's not right. Fuck. Somewhere, somebody sets this guy. B interval... We're looking for, like, B interval equals. B interval equals. And we're looking for that, like, USB config.c. This looks promising. So where am I here? This is in USB parse endpoint. Okay, so this is almost certainly where I'm looking. So B interval equals n, where n is something. Jesus. So he checks if he's high frames. Oh my lord. I see. Okay, so he like checks if it's a high speed device or a super speed or a super plus speed. And if it is, then he sets it to like interval times 8. Jesus, this is complicated. Okay. I've changed my mind. I'm not going to handle multiple polling rates because this seems way more complicated than I thought. So that's an easy fix. Easy fix. Gave up. Okay. The other thing that I wanted to do was I wanted to fix the like piping of endpoints. So here, in our mouse driver, I'm going to submit a PR for StreamOS that replaces it with the Linux kernel. Job done. I mean, that's a job done for sure. Maybe not the job we want done, but it's something. Okay, so in our mouse driver, when we send USB packets, we're just hard coding endpoint 1, and that's not like really correct. What we should be doing is we should be looking for a very specific endpoint, right? Because like the mouse could advertise as an endpoint 2 or 3, where endpoints are like, how do we describe this? You can imagine a USB device as having like multiple ports on him. This isn't like true. They're not really like ports, but they're like you like address within a device which one you want to talk to, and when like your USB system, when he sends a packet, he'll like send it to one of these guys specifically, and what the response will be depends on what they describe themselves as. So our mouse driver should like search for the appropriate endpoint to talk to, and so what we should do is we should say let endpoint, we'll say let endpoint is equal to find appropriate endpoint for the device, given the USB service handle. Okay, and what does that function look like? This is an async function because it's gonna have to talk to, like, send out USB packets. And this is a device is a USB device, and the service USB service is a USB service handle. Oh, I guess we should also say that we're doing this now. So for YouTube, we'll say that around here we were starting to work on proper mouse endpoint discovery. And what's he going to do? He's going to say, USB service, could you please get me your configuration descriptors for my device's address? So we'll say, let configurations equal this guy. This guy returns this is like a little abstraction I did off screen yesterday that just gives us like an iterator of all of the configuration descriptors. So here we say for descriptor in configurations.iter, I think is what I called. Oh no, it's in and configurations, I think. Yeah. So we're gonna look for the interface that corresponds to us, which we already did over here. So we'll do this. So we'll like look for an interface. So the way this works is this returns like a chunk of stuff, and it'll say like configuration, interface, endpoint, and it might have like multiple endpoints per interface, and then it might say like next interface, and like this interface has these endpoints. And so like the way this iterator works is like I'm kind of iterating like this, or maybe like this is a better way to draw it. But the problem is that like these endpoints are only associated with this interface. So what I have to do is I have to figure out which interface I care about and only check the endpoints for that one. So what we'll do here is we'll just say like let mute in relevant interface is equal to false. Here we'll say if we find an interface, we'll say in relevant interface is equal to this. Right, so this is the rules for if you're a USB mouse. Is like your interface class is 3 for HID, subclass says that you're a boot device, and your protocol is 2 for mouse. We need to use this like USB descriptor type. And now we can say if let USB descriptor endpoint is equal to descriptor. I guess we need to put like little ampersands here. And we're in relevant interface. Then we can start looking for the endpoint number. So we'll say, I forget what's on this guy. Does this guy tell us if he's an interrupt endpoint? He must. So we'll just quickly look on here. So he's attributes and interval. That's right. So we say endpoint attributes. We'll say attributes is this. And these guys all have to be public. So we'll just make these guys public by saying replace function with pub function. And we'll say here, I think that the attributes will say if one of them will say if it's an interrupt endpoint. Yeah. So I guess maybe attributes isn't what we want to advertise here. We don't want to advertise like transfer type. And he returns a transfer type. And we'll say self attributes get bits 2 bits at 0 shift. And Okay, so what's he bitching about? No method get bits. Is that because we don't have get bits in here? Where are we? We're in the USB module. So here we can include our bit manipulation library for get bits. That's easy. And here we'll say if it's 0, it's a transfer type control. 1 is isochronous. 2 is bulk. And 3 is interrupt. Okay, now we just have to like make this transfer type thing. So we'll just shove this here. Pub enum transfer type. And there we go. Oops, this shouldn't say ball, this should say bulk. Okay, and now we can go back into our mouse driver. And we can check the transfer type. So we'll say endpoint transfer type. So we'll say if endpoint transfer type is equal to transfer type interrupt. We only want to use interrupted transfer types for this driver. We need to derive debug, EQ, and partial EQ here for that to work. Here we would return endpoint.address. Now I have to get a little tricky here because the endpoint address is like in this like fucked up format where it says if it's an in or an out. So we'll just fix this endpoint address thing to return an endpoint address, which is, it just has in or out, but each of these will have a address associated with them. And so now we just say, we determine which one it is based off of the top bits. We'll say val get bit 7. We'll say let address is the lowest 4 bits. So 0 shift 4 bits. If it is 0, it is an endpoint address out. And if it's 1, or sorry, this should be false and true. If it's 1, that's an input. So we have if the transfer type is interrupt, and we are an input endpoint. We have to check this. Match endpoint address, and if it's in address, we return the address. Otherwise, we continue. And this is endpoint address in, I think, which comes from USB. And probably has to be made public. It already is. Sick. And this is going to return an option of U8. And if we get through all of our endpoints, we don't find the one we want, we return none. Okay, cargo check. Let expressions in this position are unstable. Fuck off. So I guess we do it this way. If not in relevant interface, we continue. So that gets rid of some of this nasty if. Then we can get rid of this one by saying let endpoint is equal to match descriptor. And we say if we're a endpoint descriptor, we continue with endpoint. Otherwise, we continue. And then I think that is simpler. Well, simpler by some metric. The compiler and the clinter are getting less angry about that. And I guess this shouldn't be a match. This should be an if let. I don't like the like quadruple nesting, so I guess we'll just do the same thing we did here. We'll say if endpoint transfer type is not equal to transfer type interrupt. Continue. And this is like an if let. Endpoint address in endpoint is equal to, or address is equal to this. Return some address. There we go. That's nicer on my eyes specifically, which is all I care about. Cool, cool. So now we have this endpoint, and we should be able to say endpoint is endpoint. And this has to be await. And here we should say expect failed to find endpoint. Now this is probably something that should be like a not crash my kernel type of failure, but again, I'm taking shortcuts today. Oops. Let's not put this in less, and let's see what's bitching about. It doesn't like this, so in UHCI 616. Nope, it was yeah, 616. What the heck? Oh, USB mod 616. We just forgot to cover the other types, so we just say assert false. I guess theoretically this could be something else, but I guess we'll just write transfer type unknown. That seems fine. Okay. Does this compile? It sure does. Do we get the right endpoint? If the mouse works, then we did in fact get the right endpoint, which we did. So we're chilling. We are chilling. All right. So I think I'm happy with that. I don't think I want to work on a keyboard driver right now. I was thinking about it, and I was thinking like, well, if like all this stuff got done in like 20 minutes, 30 minutes, then like we would need to fill some time, and making a keyboard driver was like the logical next thing to do. But I think we're like 1 hour, we're almost like an hour and a half. So I think that's like a fine place to call it. I think tomorrow, I think that we've got enough stuff to finish off the meme where someone on YouTube comments said that I couldn't run Doom, and now that I have a mouse driver that works pretty well, I think I could run Doom. And so I think tomorrow I'm just gonna try to like temporarily replace this Brick Breaker game with Doom because it's like kind of just funny. And then after that, I'm not sure. I'll have to think about like what's the next thing on the list that I want to accomplish. I think I mentioned a few of like the options at the beginning of the stream. I've been thinking about like maybe file system, maybe start working towards user space. I have like some like driver instantiation stuff that I want to clean up. It would be kind of cool to like get some confirmation that if I ran this into like with less devices plugged in that didn't crash, and like if I ran this under VirtualBox, do I get the same thing? Like we could start working towards like real hardware support. Yeah, so those are like the things on my mind. If you liked what you saw, I stream most days at around like 1 or 2 o'clock Pacific time on Twitch. If you're watching on Twitch and you are not here for the live streams and you want to watch anyways, there's a YouTube channel linked in the Twitch description that all the VODs go up to. And if you're watching on YouTube and you want to pop in, say hi, chat, whatever, there's a Twitch link in the YouTube description. All code eventually ends up on my GitHub for this StreamOS project, in like a more polished state than you see it on stream. So if you're interested in browsing the code directly, my GitHub name is the same as my Twitch and YouTube name. Yeah, thanks for watching. Catch you in the next one. Bye.